Good morning, all, and hearty welcome to the generic talk series on artificial intelligence and machine learning principles and applications in core engineering branches by Dr. STG Raghukanth, Professor, IIT Madras, Department of Civil Engineering. Now, I request our Honorable Principal, Dr. K. A. Mohammad Junaid, to welcome the gathering.
Thank you, madam. The most respected chief guest of today's generic talk series, Dr. STG Raghukanth sir from IIT Madras, esteemed advisor of RMK Group of Institutions, beloved HOD madam, faculty members, students, and my dear parents. On behalf of our respected chairman sir, all the members of the management, faculty members, students, and my own behalf, it's my great pleasure to welcome you all to this generic talk series number 10, organized by RMK Engineering College. Really, we are very fortunate to have such an eminent personality, Dr. SDG Raghukanth sir, a distinguished professor from IIT Madras, who is going to enlighten us on the fascinating topic artificial intelligence and machine learning, principles and applications in core engineering branches. My dear viewers, as we are going to continue to strive in this world for getting excellence in education and innovation. So definitely, this talk series, generic talk series, organized by RMK Group of Institutions, with the very strong motivation and support of our management, particularly our chairman sir, definitely, which will aim to inspire and empower our community to embrace the latest advancements in technology. I would like to extend a very warm welcome and thanks to Dr. Raghukanth sir for accepting our invitation to deliver a talk on artificial intelligence and machine learning, particularly for core engineering branches applications. Thank you very much, sir. Welcome you, sir. I also would like to welcome our respected advisor, sir, Dr. M.S. Palaniswamy, who is the constant support for all of our activities, particularly with respect to academic and research activities. Welcome, sir. Thank you, sir. I also would like to thank and appreciate the efforts taken by all the faculty members of Civil Engineering Department and HOD, Dr. Binu Sukumar Madam, for organizing this event by bringing eminent personality, Dr. Raghukanth sir, to deliver a talk on artificial intelligence and machine learning. I encourage and invite all the HODs of RMK Group of Institutions, faculty members, students, and parents to join this online talk series through YouTube channel, which is to be telecasted today at 10:30. So let us all come together to explore the exciting possibilities in artificial intelligence and machine learning. Thank you for the given opportunity, and let the knowledge sharing begin with the help of our eminent resource person, Dr. Raghukanth sir. Thank you for the given opportunity. Thank you.
Thank you, sir. Now I request Dr. M.S. Parnichami, Advisor, RMK Group of Institutions, our Honorable Advisor, to felicitate the gathering.
The distinguished chief guest of this generic talk series, Dr. Raghukanth, Professor from IIT Madras, learned Principal Dr. Mohammad Junaid, my colleague HOD Dr. Binu Sukumar of the Civil Engineering Department, faculty members and HODs of our group institutions. I also join our referred principal, Dr. Mohammad Junaid, in welcoming Dr. Raghukanth to deliver this very important lecture series on AI and ML applications in core engineering branches, which is very, very much vital in this particular situation where the IT and CSE computer science play a great role, not only in industries and all, but also in the students' mind for the recruitment. So this series, this talk definitely will be useful for motivating our faculty members as well as the students to apply the principles of AI and ML in core engineering branches also in their own projects so that the industry can be attracted towards core engineering to recruit the students in the coming years. In addition, this talk on AI and ML applications in core engineering will motivate the faculty members to go ahead in interdisciplinary area research, combining AI and ML and core engineering branches principles in their projects and also in their research publications. They can also go ahead for submission of research proposals covering interdisciplinary area of core engineering and IT and CSE, particularly AI and ML. For that particular purpose, this talk will be very much useful. With these few words, I once again welcome Dr. Raghukanth, the IIT Madras, my own alumni, and Dr. Binu Sukumar alumni, alma mater, to welcome and deliver this talk on AI and ML principles in core application of principles in core engineering branch. Thank you very much.
Thank you, sir.
Thank you, sir. Now, I request our beloved HOD ma'am, Dr. Binu Sukumar, Professor and Head, Department of Civil Engineering of RMK Engineering College, to introduce the chief guest to the participants.
Thank you, Aishwarya. So, good morning, all. And it's my pleasure to join with our principal sir and advisor sir in welcoming Professor Raghukanth to this August gathering. And I'm indeed thankful to Professor for accepting our invitation to give a talk on this new topic on artificial intelligence and machine learning and its application for core engineering branches. So let me give a brief introduction about Professor. He has graduated in civil engineering from JNTU during 1998 and MTech from NIT Bhopal in applied mechanics and completed his PhD from IIC Bangalore during 2005 and started his career as assistant professor in the Department of Civil Engineering IIT Guwahati in 2005 and joined IIT Madras during 2008 and as assistant professor, and now he is a professor of Department of Civil Engineering IIT Madras. And his primary R&D interests are structural dynamics, random vibrations, machine learning, steel structures, earthquake engineering, and engineering seismology. He has developed empirical and mechanistic model for simulating earthquake and their ground motions. He is also involved in developing the seismic zone map of India based on the probabilistic seismic hazard analysis. He is a principal investigator for 9 sponsored research projects funded by National Disaster Management Authority, Department of Science and Technology, Ministry of Earth Sciences, and Department of Atomic Energy, and so on. She has been a member of a working committee of experts on seismic hazard, NDMA, Government of India, member of the Indian Meteorological Department, member of Atomic Energy Regulatory Board on estimating seismic hazard for nuclear power plant sites. He has published more than 72 reviewed journal papers and 80 conference papers. And he has mentored graduate students and guided 3 PhD and 1 postdoctoral scholar and 2 MS scholars. And currently he is guiding 10 PhD scholars and 2 MS scholars. We are extremely proud to have such an eminent person to give a talk on the current topic in machine learning, artificial intelligence and machine learning, and its applications in core engineering branches. So thank you so much once again for accepting our invitation, sir. So we are eagerly waiting for to hear from you, sir. Thank you.
Thank you, Matt.
Thank you, ma'am. Now I request our speaker of today's session, Dr. STG Raghukanth, to deliver his session. And the participants who have joined through YouTube live streaming, you may please post your queries in the chat box and it will be answered by the speaker at the end of the session. Thank you, and over to you, sir.
So my screen is visible, right? Yeah.
Yes, sir. Yes, sir.
Yes, sir.
No. So anyway, so good morning to all of you. So first of all, I would like to thank RMK College, the chairman, principal, and of course, Dr. Vinu, for inviting me to this seminar. Okay. So now, of course, as you have mentioned, this nowadays, AI and ML are becoming very popular here. So I will be showing some of these AI and ML techniques, which we have also used in earthquake engineering. I will show some applications also and how the subject is going forward and what we can, do in our civil engineering and earthquake engineering things also. Okay. So basically what has happened was, as you know, right? So this AI and ML has become very, very popular. So in our IIT also, most of our students are interested in AI and ML. So we also have been forced actually, okay, to develop some new courses, which incorporate this in our, in our civil engineering itself. So that the students can learn and we also can learn the subject in a better fashion also. Okay. So I have floated a new course, in our civil engineering last year on seismic data analytics, where we speak essentially about AI and machine learning in earthquake engineering applications. Okay. So these are, I'm just for, all of you, I'm just showing these are some of the textbooks actually, which are available, nicely. Any of you can, the soft copies are also available. Okay. So you can download if you want to know the subject also. Okay. And these are some reference books also. I'm showing it to you for, to more understanding. Okay. Then there are a lot of YouTube videos are there. Okay. So he is a Professor Andrew Ng, he's a professor in Stanford, very famous in machine learning, artificial intelligence. His YouTube videos are also there actually. Okay. If somebody wants to know the subject from a computer science person, say, okay. So his videos contains a lot of mathematical details, and they also give some Python and MATLAB codes also, where anybody can start actually using machine learning in their own problem itself. Okay. So now, anyway, let us come to our thing. So why do we require this AI and machine learning in civil engineering? That's what we are all discussing today. Of course, one thing is nowadays it's a very popular subject. I know, most of the students, I think everybody wants to do AI and ML. There are nobody, coming for civil and others also. So we also have to change slightly our alignment actually. Okay. And of course, nowadays students, employees, researchers, you name any person, everybody wants AI and ML. And even in our IIT Madras, we have online BSc program actually for, data science and others. So everybody is, these things are becoming very popular nowadays actually. Okay. And then of course there are some data scientist jobs, they are there, it seems, they're very well paid compared to others. That's why, all this rush is happening actually. Okay. And now if you see these applications where, AI and machine learning are right now, like directly used in practice. Okay. So everybody would have shown this web search, e-commerce. You would have seen in WhatsApp itself, you have a Meta AI is there. You can ask any question, it chats with you, you followed. So all the information. Then in space exploration, say, without artificial intelligence, they can't do anything actually. Okay. Because the communication itself takes so much of time. So the robot itself has to take a decision on its own actually. Okay. So there are a lot of applications are there in space, e-commerce websites, web search, YouTube, all of you would have, seen in your things itself. And in computational biology also, say, to develop new type of medicines, some many combinations also this AI has been used. And social networks, robotics, image signal processing, right, face recognition. Nowadays, attendance also we are taking, with this thing itself. So all these details are, everybody is, using this in our things itself. Okay. And now, when it comes to civil engineering, say, see, the problem is, research papers are there actually. Okay. But If you go to any design company or any this one, they are not directly using it. Maybe into under some few years, this may have to be used here itself. Okay. Now, when it comes to earthquake engineering, say there is a lot of scope for AI and ML because we will be directly handling with the data itself, and there are a lot of applications in practice. Actually, I will show some of these results in today's the lecture itself. Now, if you see in our civil engineering, say the starting, like when I studied my undergraduate also. So, like in civil engineering, whenever you want to analyze any structures, a beam, column, or anything actually, the first thing what everybody says is you should write the equation of motion actually. Okay. So, like for example, these are the equations of motion, written in terms of stresses or in strength of materials. Everybody would have seen this one, plane sections remain plane, simple beam theory. So you have to write a differential equation. Okay. Then you have these boundary conditions are there. Now, once you know the boundary conditions is there, so you solve this equation and then try to find out the solution actual. Okay. So you have analytical, FEM, all kinds of methods are there. So this is what traditionally, we use in our civil engineering. Essentially, in most of the cases, actually, equation of motion, boundary condition, you find out the solution actual. Okay. But the problem, we all know in our civil engineering is when you want to do these mathematical approaches, these equations are based on, a lot of assumptions actual. Okay. Like plane sections remain plane, homogeneous, elastic, you can get these type of solutions itself. So when you like to use these equations directly in practice, most of you would have seen, there will be a huge, scatter or, disagreement, things will come into picture. So what we do in our civil engineering, one more thing is we do a lot of experiments also. Okay. So like, for example, if I want to find out buckling load of a column, say, okay. So you would have studied pi square EI by L square, but that formula directly, we can't use it in, practice actual. So what one does is we do a lot of experiments actually. We test a lot of steel columns or something in the lab. You plot the data, say. So for the data, you will fit some type of a equation actually. So this equation generally, the functional form we take from the mechanics, like pi square EI by L square itself may be fine, but some constant here, there, something we will add it and then develop a equation actually. And finally, we will derive this type of empirical formulas also, which is a combination of experiment as well as mechanics. So these formulas are right now in your IS 800, IS 456. If you open up, say, most of the formulas have been done as a combination of experiments as well as, some little bit of mechanics actual. Okay. So this is how we try to do this one. And then when you look at the building codes, the wind load, earthquake load calculations, if you see, I hope you would have seen IS 875 part 3 or something like that. That is for the wind load. You will see they will give this wind zone map, something like this. So these zone maps are purely based on data actually, some of the observations. And then there are a lot of pressure coefficients, lot of things have been given in the IS code. So they all come from empirical only, from experiments like wind tunnel test. Directly you use this and then get this type of numbers itself. Okay. Now, when it comes to seismic zone maps, today I will be showing some of applications of AI in this area. So this also is purely based on data actually. Okay, so there is no mechanics, these are purely based on data itself. And then all of you know this design response spectra actually. Okay, so where you have x-axis which depends on the natural frequency of the structure, and your y-axis will give you the spectral acceleration, say. Okay, which if you multiply by these quantities, you will get the seismic coefficient itself actually. So the spectras and all those things, they have come from, data only. There is no mechanics has been used, in obtaining these curves itself actually. Okay. So like all past data they have used, and then, some averaging, something has been done, and then they have got this, all these things itself actually. Okay. So now, so to just summarize, say, so right now in our conventional engineering, when you come to building codes, when you want to do something in practice, so experiments are very, very important for us. That is the data actual. Okay. So the data is very important, for doing this, the experiments. So now in our civil, now right now, what is happening is, the most important thing what has happened right now is the sensors have become very cheap in our, nowadays. Okay, because of some China or whatever here, where the sensors have become very cheap. So like for example, you can buy a strain gauge, say, for 100 to 200 rupees itself. Actually, okay. So good quality strain gauge means maybe 500 or something. If you pay, you will get a strain gauge. And nowadays, everybody is having a mobile phone. In mobile phone, all of you would have seen, if you buy 10,000 mobile also, you have a lot of sensors are there, like accelerometer is are there, You followed gyroscopes are there, GPS is there, there's so many. So instrumentation has become very, very cheap nowadays, actually. So the advantage is when you have when the instruments have become very cheap, say, so affordability will be high. So now everybody can buy this and they can do the tests, actually. Okay, so nowadays 10 to 30 years back, say, if anybody wants to do experimental research, they used to happen only in NITs or IITs only, because they only used to afford these things. But now because things are becoming very cheap, so now if you go to any colleges, say, state level or local colleges also, people are doing very good experiments, actually, because sensors have become cheap. A lot of experiments are being done, and huge data set is becoming available nowadays, actually followed. So now our research is also, if you see, the databases are increasing day by day, actually. Okay, and then high performance computing, say, so this also is increased. So see, now your mobile phones itself have 8 GB RAM, actually, which has very powerful computer itself. So now our computers are becoming very powerful, and then data sets are also increasing very high. So this is my most the important combination, actually, which is making AI in civil engineering very, very popular nowadays, actually. So I'm just showing you some examples, where right now people are using, like this is a very tall building in China, actually. Okay. And nowadays, as population is increasing, there is no way you cannot grow horizontally. You have to grow vertically itself. So everywhere you are seeing is tall buildings, tall structures itself. Now here, when you want to do health monitoring of this building, says you want to find out, which beam has corroded, which bar has corroded, where, damage has happened. If you want to monitor, say, this type of huge buildings, it is very, very tough, actually, to do these things manually. So what people are doing is they have instrumented these buildings itself, because sensors are cheap and it is very easy. So like, for example, these buildings, they have put wind pressure sensor, you can see anemometer, then temperature they are measuring, vibrating wire gauge, thermometer, theodolite, all these you follow. This is this has been, this building full, every floor is being instrumented, actually. So once instrument these buildings, you will be getting data like this, actual. Okay, so continuously these buildings are being monitored, actually. Okay, so we would like to know which bar has corroded, where damages has happened or something like that, and then manually not possible, so you can do only with the help of sensors itself. Okay, now similarly, so the Burj Khalifa building, it's a very expensive building also, and it is very difficult to this monitor this the structure itself. So what they have done is, in Burj Khalifa also, every floor, say, has been instrumented. So you have accelerometer, variety of instruments have been come up, made accelerometers there, meteorological data, displacement, tilt meters, huge databases are getting from this buildings itself. Okay, so the tall build, and then since it is, they are monitored continuously, so the problem is, every second, or every 10 samples per second or 100 samples per second, continuous data is coming from this building, actually. And then in the Burj Khalifa, if you see, the data itself is around the size of 100 terabytes, actually. So huge number of data sets is coming into picture. So now the job of a structural engineer is, you have to analyze this data and then tell, where damage has been located, actually, like which portion of the buildings a small crack has opened up or corrosion has happened. So now you have to take a decision, actually. Okay, so the problem is, 100 terabyte of data means, even your ordinary desktops will say out of memory, actually followed. And then since you are having from several instruments, say, so now how do we analyze this data is a big challenge. And the challenge of a civil engineer is you have to analyze this data and you have to take a decision. This is the most challenging task right now faced by our structural engineers. And now this is also, like, as I already mentioned you, lot of since instrumentation has become very cheap, say, everybody is doing experiments, a lot of data sets are getting published. Say, like, for example, this is the column buckling, this one. So people have done a lot of experiments, solid column, tube column, this column, that column, so much of experimental data is available, actually. So now how do we analyze this data, and then finally, say, how do we make a conclusion, actually, or what should be, what type of decisions you have to take, say. So this is is a challenge, which engineers are facing, nowadays. So the most important thing is the data is becoming very huge because sensors are very cheap. And now based on this huge database, you have to take a decision actually. So this is the most challenge which civil engineers are facing. Okay. Now this is one type of problem. Other type of problems, like if you see water resources engineering or hydrology also, like, rainfall measurements. You would have seen Delhi, very high rainfall came, I think 2 days back, airport collapse has happened or something like that. So now, like, for example, say here also the rainfall in the rain gauges are, put up. Lot of data is coming, like from 1871, we have the data set itself. So now the challenge for engineers, say, is, how do we forecast actually? If I can forecast, say, very heavy rainfall or something, before at least 2-3 days before, so we can take some decisions or we can protect some of our infrastructure also actually. Okay. So these are some of the challenge, and all these things you have to do just based on data. No mechanics is, involved actually. So this is a challenge. And now coming to earthquake engineering, say, where I will be showing you some few applications. But of course, the same thing can be translated. You can use for any discipline you want actually. Okay. So now in earthquake engineering also, we know earthquakes only through their, instruments only. There is no mechanics or mechanics is it, but it is giving very less, where the data itself becomes very important in earthquake engineering. Nowadays, what has happened was because sensors have become cheap and people are able to afford, say, so the whole world has been, instrumented actually. Okay. Variety of instruments are there. There are instruments which can measure accelerations. There are instruments which can measure velocity, displacement, all kinds of information. So, instruments are available. So now since affordability has increased, sensors have become very cheap. Our, things have gone up. So whole world has been instrumented actually. Okay. So like, for example, you can see these stations in Google Earth itself. You can open and you can see whole India, say, so many instruments now are working. Continuous monitoring is happening actually. Okay. So like this is Europe, you can see most of the Europe, say, every maybe 10 kilometer or 5 kilometer, there is an instrument actually. Okay. So if anything happens, say, not only earthquake, like a traffic vibration maybe, or it may be some, explosion or any impact or something also. So the whole, it will be recorded through this instruments itself. So you will know the data also within seconds itself. And they are all linked to satellite. Immediately you can download this database on your computer also. So this is United States. You can see in USA, it's fully instrumented actually. Okay. So every 50 kilometer or, you have an instrument in United States. Anything happens, say, it will be recorded in the seismographer. Now this is Japan. You can see Japan is the most, instrumented place. You can't see even the, the Japan boundaries because, you can see full of instruments. Every 100 meter, 200 meter, you have an instrument. They have put instruments on the surface, on the bottom, several depths also. So you will be getting, and they're all linked to satellite itself. So you will be getting continuous monitoring of the data. It is same as our health monitoring. I showed you Burj Dubai also. So that continuously the Burj Dubai is getting monitored. We will be getting data set itself. So now the problem is we have to analyze this data and then we have to take a decision. Actually, that is a challenge here. So now, and of course, in earthquake engineering, we are having almost 10 lakhs or more number of data sets are coming into picture. So now huge databases. So now we have to analyze these databases and then we have to take a decision. That is a challenge which we are facing actually. Okay. So now the problem here is like this. So now I'm just showing you 24 hours. You can see the x-axis, okay, and your y-axis is amplitude. So this is one instrument, real instrument record. So 24 hours it has monitored. So the data looks like this actually. So you will see this type of spikes, one spike here, small spikes also like this you will see here. Now, when you look at this database, all because we are all human beings, right? Our eye automatically, it will go to the largest thing actual. Okay, so we will look at these largest things and then we analyze it. These small spikes. Say you can see here are the small spike. Generally, our human, we will not be able to notice actual. Okay, so these things. So now these are very difficult to detect. So generally, when these things are analyzed by a human being, say with these small things, we neglect them as a noise kind of thing actually. The large things we think it is something like a signal and we try to analyze. Okay, now I am showing the data for 24 hours like this. You are having for 10 years data sets, say, and you have to take a decision. It becomes very difficult difficult actually. Okay. So the problem is these small events say, so they only play a major role actually. Okay. So like, for example, when the building is getting damaged, say, so the crack also, when it is getting formed, it will be very small in the starting stage actually. And then slowly it expands, So now when you can detect the crack, when the crack was very small, say, or when the corrosion in the beam is very small, then, the repairs can be done very fast and you can save a lot of money actually. Okay. But the problem is we will not be able to detect when the cracks are small or corrosion is small, because our human, too much of data sets and this thing. So we try to ignore this data and then we try to detect only when things are becoming very high. And then, like, for example, if you see these buildings and when you detect here the big one, the crack would have, very big crack would have happened and repair strategies, would have been very expensive actually. So the idea is when things are very small, say at the initial stage itself, if you can detect, you can save a lot of money and you can do a lot of things itself actually. Okay. So like, for example, if you look at it as an earthquake, say, these small things may indicate, something like a foreshock actual. So if you can detect that they are all foreshocks, say, you can give a earthquake early warning and say that large earthquake is going to happen maybe in the next 1 or 2 days, so that, you can save some lives and, the property itself. So the problem is, so humans, we fail actually in analyzing these small events, but we are very good in analyzing, large events. Our eyes automatically search for them. We can take decisions. So this is where machine learning comes into picture actually. So the main advantage of machine learning is, so 100 terabytes of data, say, if we give it to any human being, he will not be able to analyze actually. So what the philosophy is, 100 terabytes of data will be given to any machine learning algorithm. It analyzes 100 terabytes. Finally, some 1 GB of data or some important things, if it can shortlist, say, then we, a human being, can analyze and we can take decisions. That is a philosophy in our, this engineering. So like, for example, these are some databases I'm showing you. See, some instrument data I'm showing you here. Of course, these are earthquake, but you can take it to be buildings. Similar data sets will be there. So now if you look at these databases, say, they look entirely different actually. Okay. So like, for example, here, high frequency, low frequency, variety things will come into picture. So now as a human, as a prime engineer, say, I have to analyze this data and I have to tell. See, like, for example, when I look at this time history, say, what does this time history tells me? Whether there is a crack in concrete or crack in steel or some corrosion in this one which has happened. So we have to give all this information itself. Okay. So now how do we estimate some useful information? So this is a challenge. So using this database, so now you should be able to give, the useful, information. So like, for example, what are the parameters, which I can estimate from the data and which are useful, and I can take some decisions. So this is a challenge. So here the machine learning comes into picture actually. Now these are some of the databases I'm showing you in earthquake engineering. So in 1980s, we had very few records are there. Now, as the time is increasing, as already I told you, people are able to afford these instruments, and now we are having exponential increase in the databases right now. So the instruments are almost, 10 lakhs or 1 crore. Huge databases have been, come into, it is increasing actually. And if you look at in the future also, so you will be able to get, huge amounts of database. So the challenge is, how to analyze this huge databases and then make some, useful conclusions actually. Okay. So this is where, this AI comes into picture, and machine learning will, help us, in taking some meaningful decisions actually. So now anyway, coming to, so this exponential growth is happening. So now how do we develop, these complex relations with this database? So now coming to this earthquake engineering, I'm showing you, like, there are something like 13,000 databases are there. So now how do we use this type of data and come up with some useful, conclusions? So this is a challenge. So these are some of the earthquakes actually, which has been recorded in the database. So now we will be analyzing this data and we will come up with some useful conclusions. Okay. So these are some histograms, some of these things. And now these are from the Indian side actually. So in India also, we are having a lot of instruments, continuously the things are getting monitored here. So now using this database, we have to take a decision actually. Okay. So like, it may be earthquake early warning, or it may be a design response spectra, or which can be used to calculate seismic load, and you can design your structure also. So this is the challenge. Okay. And now, generally, what we do in our civil engineering, say, whenever somebody gives you data, the first thing what people do is, they will do regressions, actually, okay, linear regression. So we try to fit, you see, y is equal to mx plus c. So these type of equations will be, generally we use that, okay, to fit this database, okay. But since that, so these equations are fine when the data is very, very small. But when the data is increasing, say, huge amounts of data, so the simple equations, will be very, tough. Means the scatter will be very high. They may not able to give, a proper, estimate of your things itself. Okay. So now in seismic, people have developed, you see, complicated functional forms actually, okay, to explain the data. And these complicated functional forms, say, they have something around, like the constants, C1, C2, C3, C4, like this 400 to 800 constants, are required. And then although the constants you are increasing, say, but, the standard deviation is also extremely high when you do these ordinary regressions, on this database actually. So now here the question is whether artificial intelligence can I use, to model this data, and whether I can explain the data, say, with less number of unknowns and with less standard deviation. So less unknowns, so this is the challenge actually. So we want to develop a neural network which can explain the data with less unknowns and with less error. So this is the, the main thing. So whether, yeah, this is where ANNs comes into picture actually. Okay. And now this is what I told. So the simple functional forms, say, when you develop simple equations, so this is the curve actually. So these black lines you are seeing is a curve, and these are all the databases you can see. So when you do simple equations, you will have a huge scatter actually forward. So this equation, say, so this equation gives you, at this distance, this is the value, but you can see a huge scatter. So the simple equations, cannot be used, or they are not reliable, in explaining these databases. So the question is whether ANN can solve, these type of problems. So they can explain the same data, say, with less number of unknowns itself, and then the scatter also should be captured by your neural network. So this is a challenge. So now in machine learning, most of, so now this is becoming very, very popular here. So there are a lot of, things are there in machine learning, like supervised, unsupervised. You can use these techniques, say, for regression equations, classification, you can use this one, the dimensional reduction, you can do clustering, you can do. So a lot of applications are there in our artificial intelligence. Okay. So let us see these things in detail. So now generally this machine learning says, so there is one, a famous theorem is there in mathematics actually, which shows that these neural networks, they are universal approximators actually. That means, they can mimic any continuous function. So there is a mathematical theorem which says that, machine learning or this neural networks, say, so they can handle any type of data set itself. Okay. And they are very good in capturing, the nonlinear behavior also. And when you are having huge databases, say, so they can extract, the useful information from these databases. And the most important thing in machine learning, the main requirement is the database should be extremely high actually. So when the data is extremely high, they work very well. When the database is very small, say, then machine learning has, the problems actually. So, and of course, it can handle images also. Now you are saying images it can handle data, it can handle anything, as inputs, and it can provide you, useful things itself. So now in machine learning, so there is what they call as a supervised and unsupervised also. So unsupervised means, it is all, there are no labels actually. It is something like the natural data set. So whenever you are having natural data sets, they are all unsupervised actually. So you don't have control. But when you are doing in civil engineering, so when you do experiments, we plan nicely. Like for example, the length of the beam, we plan, width of the beam, we plan, and then what should be the compressive strength and other things we plan. So that's what we call as, supervised learning, or, which comes with the labels itself actually. So this is a supervised, unsupervised, both also neural network can handle when you're having data with labels actually, like regression equation. If you want to know, like, which is a dependent variable, which is independent variable, you can handle. And unsupervised data, so when you don't have any labels also, these ANNs will be able to handle both the set type of data sets. So now this is one of the earliest, the first neural network you can say, which was done in 1943 actual. Okay, this is what they call as McCall and Pitts model, they say. So he was the first actual to develop this concept of the neuron actual. So what he did was, these are all the inputs, say x1, x2, x3. So these are the inputs actual. Okay, so this is an output. This is a neuron which is here. So what he did was, he gave weights actual. So it is like a weighted average, W1 into X1, W2 into X2, W3 into X3 you take here. And his output here, based on this, he takes something like, 0 or 1 like this, he developed this function in long back actual. So now this same thing now has been expanded, and now, we are using for our purposes. So now the same thing, so this came into picture, the perceptron model or whatever, we use here. So this is concept is same. So instead of step function, say, we use some other complicated, the nonlinear function like sigmoidal functions or tan hyperbolic, or if you want linear, say, you can use linear function itself. So this model came up somewhere around, 1962. So this became the building block actual for, this neural network. So this is a basic building block, so they defined what is meant by neuron. Now using this one, the neural networks have been developed. So now this is what we call as the feed forward neuron itself. So you are having a lot of inputs to say, okay. So you multiply them by weightages you give. You can add a bias also to this output here. So once you have all the inputs to say, so g of x actually, you can sum up all these things, and then y has to be estimated. So this y is written as f of this wx plus b, and this y can be taken as nonlinear 1 by 1 plus sigmoidal function and other things can be used actually. So you can see that is how the information flows. So you have input layer, then hidden neurons are there. So you weighted averages, you take it and then do a nonlinear transformation, and then you pass on to the next layer, and that will be passed on to the output layer itself. So this is what we call as the feed forward neuron itself. And now in machine learning, so there are some keywords are there actually. So the keywords are nowadays, what we use, what we call as, the input layer is there. So there are basically input layer will be there. Then we have what we call as the hidden layers actual. Okay. So then we are having the output layer. So whatever we want to inputs are here, output are there. And in between, so you will have hidden layers where this non-linearity, the complex things, say it can go into this one actual. Okay. So this is what we call as generally a network or, the architecture itself. And there is something like, we use what we call as a minimum cost function or loss function we use. So this is nothing but, a simple mean square error actually, okay, which all of you would have used in regression. Like, this is the data and this is a prediction actual. You just find out the error here and you take square root and then you mean value this one. So this is what we call as a cost function or sometimes loss function. But anyway, this is just the error function also, you can call them actually. So this is what a typical neural network does actually. Okay, so you are having inputs to say. So you will take some hidden layer. So this you have to choose based on the complexity of the problem, and you are having output actually. So I am showing you a simple neural network which is having only one hidden layer and neurons actually. Okay, so like now this hidden layers HJ. So the input to the neuron comes like this actually. Okay, you can see. So all the inputs are weighted. So you have to put a bias here, and then you do a nonlinear transformation, say, you will get HJ actual. Now, when you want to compute YK, say, YK is connected only to the hidden layer side. So you take all the hidden layer weightages, and then you multiply by them, you add a bias, and you do a nonlinear transformation, say. So you will get this YK actual, okay? And then here to find that, so the unknowns here are the weights actual. So how much weightages, I have to use in my network, or what should be this bias act. So these are the two unknowns, which are there in our neural network. So these have to be estimated based on the database actually. So once you estimate this one, then this neural network can be used to predict, whatever Y's you want, based on your X itself actually. Okay. So the most important in neural network is how to calculate the number of unknowns. Okay. How many weights are there? How many biases are there? So this is a simple thing itself. So here in this problem, if you see, there are three input, the nodes are there, and then you are having, you see, four hidden neurons actually. So now here, so the number of weights will be, you see, m cross n. That means 4 3s are 12 actual, okay? And then from hidden layer to output layer, say. So you are having here 4 hidden, then 2 output layers. So 4 into 2 becomes, 8 is the number of weights, between hidden to output are there. Then for each hidden neuron and for each output neuron, so you will be having a bias also. So in this problem, so you are having 1, 2, 3, 4, 4 hidden, and then 2 sets. So 4 plus 2, 6 biases are there. So the total number of unknowns is, 4 threes are 12 plus 4 into 2 plus you are having, the 6 biases. So this is how, we compute, the number of unknowns in a neural network. And then the simple rule is, when the data size, you are having, let us say, data of 100 samples are there, say. So your number of unknowns should be always less than, the number of data points actually. Okay. Otherwise, overfitting and, the problem becomes ill conditioned. So this is what you have to remember. So this is the formula you can use, to find out, how many unknowns are there in your neural network actually. And then to find out the weights, say, because you have incorporated the nonlinearity and other things. So there are a lot of algorithms are available, optimization algorithms are there, and back propagation, they call with several names, Adam optimizer or Levenberg market algorithm, global optimization algorithms are there. So where you can use this algorithm, say, and you can easily find out, the weights and biases in your neural network. So there are a lot of, since the problem is nonlinear, say, so if it was linear, then no need to do any iterative procedure because the things are nonlinear because of the the sigmoidal function and other things are there. So you have to use a nonlinear approach, like iterative kind of approaches to find out this weights actually. So what we generally do is there are a lot of algorithms are there. So first to starting, say, we assume some weights actually, okay, and then you predict the output. So you calculate loss function, say, and then once again you update the weights actually. You can see here this is a nice animation which shows inputs are there. So from the inputs, say, forward pass they call it. Okay, so you take this one, assume some weights, you find out the output, you find out the loss function, you calculate loss, say, and then once again you adjust the weights actually. You slightly rechange the weights and once again you calculate. Once again you do this procedure until things have converged. So this is a typical thing which you try to do in our neural network. So this function, we try to minimize this one and we try to find there are something like learning rates and others are there. So these are some of the typical objective functions actually. So you have to find out where the error will be minimum. So this has to be done. So there are a lot of issues are there actually in neural networks. So some hyperparameters also will be there. Sometimes overfitting also may happen. So generally what we do, the data set, we train into training set, validation and testing set also. We try to do this one like 75%, 15% and 15%, or you can take 80, 10, 10 also, so that your network will not get trapped in local minima and to convert just to a global minima itself. So overfitting, optimal fitting, so this also you have to do. So this comes under pure the data analysis actual. So after getting the results, you examine each and everything carefully and then you go back, you revise your neural network and then try. This has to be done in iterative fashion itself. So you have to plot so many things and then you have to do, underfit, you have to check all these things. So that's why we do training, validation, and then testing also. And these are some keywords actually. Okay. So generally what we do in machine learning is all the inputs, say, we scale them, to between 0 to 1 actually. So 0 to 1 so that there will be no one input will not dominate, your entire neural network also. So then we have something like, how many hidden layers have to be chosen and how many hidden neurons have to be used also. So that also, there are a lot of methods are there, to do this, in our MATLAB. These softwares are already available to us. So you have to do it in iterative fashion itself. So then regularization has to be done, learning rate drop. So all these things has to be estimated, based on iterative process you can try here. And activation function, so you can use depending on the type of the problem. It's a sigmoidal function, say. It goes from 0 to 1, tan hyperbolic, so -1 to 1. Sometimes if you are doing linear regression or, this regression, so you can use linear type of curves also. So you can use whatever. So there are a lot of choices are available to you. So which one to use? So depends on your problem actually. Now I will just give you one small example, a toy problem actually. Okay. So since most of you will be first time if you are doing neural networks, it's very easy to implement in computer actual. Okay. So like for example, I have a small beam is there. Okay. I want to find out deflection of this beam to a UDL actually. Okay. So now this I want to find out, say. So now this problem you all of you would have done in strength of materials actually. Okay. The deflection and all those things we can find out from strength of material. Now let us say this problem I want to use by neural neural network actually. So in neural network, say what you require is, the data has to be generated here. So what to do is, we generate a lot of data, say from your mechanics or finite element or whatever. So I will create a network like this. So I will take in input, W is the input, Young's modulus, then moment of inertia, 3 inputs this thing. And then my output layer is, the deflection actual at 0 meter, 1 meter, 9 meter, and 10. Anyway, of course, at the supports, the deflection is 0 only, but just for, say this case, I've just illustrated here. Okay. So 3 input neurons are there, 4 hidden are there, and then 11 output neurons are there. So you can find out the total number of unknowns also. 3 into 4, and then 11 into 4 will be the weights here. Then you have biases actually. Biases are there only for the hidden neurons and the output layer. So 4 plus 11. So the total number of unknowns in my network is 71 actually. So if the number of unknowns are 71, so my data set should be more than, I should have more than 71 samples. And that is a simple thumb rule actually. Okay. So now using this ones, I will run my neural network, and then this is a small MATLAB code I am showing you. Very few, with just very few lines, you can generate your own neural network in MATLAB. Of course, in Python also you can generate this one. So now this is how the simple code actually. You can see very few lines are there. Okay, so train ratio 70%, 15%. You give this one, and you train it. Say automatically the network gets trained, and these are the comparisons actually. Okay, you can see the analytical thing is that green line, just a dotted line comes from the neural network. Of course, this problem is a simple type problem. You can see neural network can perfectly, mimic this entire, the deflection profile for a beam itself. Okay. Now, this is one more network, say, which you can find out in this paper. So they have tried, to find out, the compressive strength of concrete, say, using a non-destructive test. Actually, say, like, for example, when a structure is old, and if you want to assess the strength of the structure, so we do this test, surface electrical resistivity, rebound, that test, this is there, then ultrasonic pulse velocity, say. So you do test in the, field, actually, you generate data. So from this database, you have to find out what is the remaining strength or, of your structure itself, actually. Okay. So right now we do from some other approaches, but now this person, he is trained with, neural network itself. Okay. So he generated a lot of data. He has tested a lot of specimens or a lot of structures, with age 7 days, age 28 days, 90 days age. He found out all these things, and the compressive strength he estimated from the, a lot of samples he has done, and then he has tried to fit a neural network for this problem actually. Okay. And then his results, a neural network you followed. So test results and the ANN, say both of them, they match very nicely, saying that neural networks are very capable actually. Okay. So once you have trained this network, he can use this network, in the field itself. So if you want to analyze any structures in the field, you do these 3 tests, say just feed in your neural network, automatically you will get the strength of the structure itself actually. Okay. So this is one interesting problem he tried. This database is available in his paper actually. If some of you are interested, so you can take this and you can rerun this network, and then you can confirm his results, and then you can use it for other things also. Now coming to this earthquakes, which is much more complicated here. So now here the idea is, these are the inputs, actual magnitude, distance, site, and fault type. If I know, I want to predict this response spectra. Actually. So this is the output which we have to do in our ANN. Okay. So of course, whenever you are doing data analysis, okay. So you have to find out mean, median, kurtosis, skewness, and all other things to verify that your data should be, non-Gaussian. Then only neural networks can be used. If the data is a Gaussian, say, then no need of using neural network. You can do ordinary linear regression itself. So this is one rule, which we use. Why we have to use ANN actually. Okay. And of course, earthquake data, you can see kurtosis is very high, and the skewness is also, not zero kind of thing. So which means the data is non-Gaussian. So the only way to handle non-Gaussian is, the neural network. Non-linearity is also there. Non-Gaussianity is also there. And then one more thing nowadays, what people are doing is when the data is coming from different groups, say mixed effects regression has to be done. Okay. And this also can be nicely incorporated in our neural networks also. We'll not go into details. I will just show you this. So this is one neural network which we developed, to predict the response spectra, say. So this is our design parameters, actual response spectrum, PGA, PGV. These are required for design, earthquake design of any building, actual. Okay. And these are the inputs. So now using the database, how good, your ANN can do it. So this is a neural network. So 5 neurons, 5 hidden, 28 output actual. So you can easily find out how many number of unknowns are there. So 5 5s are 25. then 5 into 28. Then you have to add biases, 5 biases here, then 28 biases here itself actually. So around some 180, 190, the numbers comes into picture for this problem. Okay. So this is a neural network here. So you run this network set. So these are the weights actually, which has been obtained from, this minimization. And these are the comparisons are there, and you can find out, you can do variety of parameters are there to check, how good is your neural network. So all those things shows that, the neural network is much more superior to conventional regression techniques actually. So these are some of the, I'm showing you the standard deviation. So the traditional equations you can see the standard deviation for PGA is, 0.754 actually. And then if you do with the neural networks, so the standard deviation is, 0.327. So that means you can explain the data with a less number of unknowns and with less standard deviation using artificial intelligence. So which shows, that artificial intelligence is much more superior to the conventional techniques, essentially in earthquake engineering. So right now in earthquake engineering, what people have done is, they have started using artificial intelligence also, and then, getting these hazard curves and then hazard maps, and then which are directly used in the design of building itself. And then you can also find out in neural networks which parameter is important actually, whether the, which input parameter is very important. So there are Garson's index, so many indexes are there. You can find out which one controls your results also. So this is what I'm showing you where this ANN has been used, really in practice actually, okay, to find out, the spectral accelerations for Shimla city I'm showing here. So artificial intelligence is doing, nicely, the earthquake loads same as the conventional approaches itself, which, and the advantage is you can explain the data with less number of unknowns and with less standard deviation. So this is a strong basis, why we have to use ANN in our, calculating this earthquake loads or in modeling of our seismic database. Now, another thing is, when you're having databases like this, rainfall, or I showed you, the hydrographs are you followed. So these type of data so where you will be having a trend actual, okay? So where you want to forecast it. So like, for example, I know the data from 1950 to 2014, now I want to forecast it to 2015, like rainfall forecast or these type of data sets, this is what we call as, the data which has a trend or seasonality. Some patterns are there in the database also. So nowadays we are having, very new neural networks which have come into picture. What they call is, LSTM actually, which they call as long short-term memory networks. So these neural networks are very popular in forecasting actually, okay, using the past data you forecast for the future itself. So these neural networks, they can even, model the memory of the database actually. Okay. So if the data has any memory, so like, for example, every 6 years, the trend is happening, or every 5 years, So this also can be modeled in this neural network. So these networks, we call them as LSTM, networks. So these are becoming very popular, nowadays. So these networks have, long-term memory. They can remember short-term memory also. Using this information, they will predict, they will forecast into the future itself. So they have something like, forget gate, input gate, waits for output gates are there. So you can use this information to like the past information, the current information, you concatenate how much information has to be removed, how much information has to be taken forward, and what new things have to be incorporated here. And then, they predict your output itself. And then, so this is a very popular networks right now, which are becoming very popular, to handle the data, which has some seasonality or a trend or, to capture memory in the database itself. So this also we tried for earthquake, this accelerations itself. So which shows that, these techniques are very, very superior compared to this conventional, the networks. Okay. And they work very nicely. And the results are also more or less comparable with the, the conventional techniques with less number of unknowns and with less standard deviation itself. And nowadays, the future, nowadays, the current situation, when you are having a small data sets actual, okay. So the conventional neural networks are perfect. When you're having, large data sets actual, okay. So then, you require these large neural networks, or people nowadays, they are calling as, deep learning actual. Okay, so deep neural networks have come into picture. So generally the neural networks can be classified into shallow and deep actual. So when the data sets are very small, say shallow neural networks are very popular. When you're having huge databases, say deep learning models also have entered and they are becoming very popular. Nowadays everybody is using in our case also. So so there are so variety of so many networks have come in this deep learning actual. One type of network is and there have been other special networks also which can handle uncertainty in the data also. So when there are a lot of uncertainties, say, okay, so in the data, so the data itself has some error, like when you're measuring, right, something, it will have some type of error. So this also can be handled, through your neural networks itself, actual. Okay. So so nowadays, I hope some of you have had this Bayesian regression, actual. So this is a very popular thing in statistics. So this method is used widely when the data has a lot of uncertainty actual. So when the data has a lot of uncertainty, so instead of going for one prediction, right, one straight line like this, we would like to estimate its confidence intervals, the uncertainty, epistemic uncertainty, aleatory uncertainty, all those things we'll be interested in estimating also. Okay. So now this also has been incorporated in neural networks also. So these neural networks, we call them as, Bayesian, neural networks, where you treat the unknowns as random variables and you find out their probability density functions, actual mean value, standard deviation. So advantage is you can find out aleatory uncertainties, epistemic uncertainties, lack of data, lack of understanding. All those things can be captured in this Bayesian neural networks itself. So they are very special networks, where you can handle the uncertainties also. So this also you can work for, for earthquake database, say. So you can get both the combinations actual, like very aleatory you can find out, epistemic also you can estimate from the database. Epistemic uncertainty, tells you the quality of your data, how good is your database. Aleatory will tell you, the inherent randomness in the database. So this also now has been incorporated in ANN, and we can easily handle, the uncertain data set through this neural network itself. Then one more networks, which nowadays are becoming popular is, the auto encoders actual. Okay. So which they call, auto encoders, which are becoming very popular, this one. So where you can do the dimensional reduction of the data, and then you can, get information from the databases itself. So like, for example, I'm showing you here. So this entire database is 91 inputs can be reduced to 3 pieces itself actual. And you can understand this, dimensional reduction. So instead of handling 91, say, you can handle 3, and you can, our understanding will become better. Like I showed you in the starting, right, 100 terabytes of data, say, can be reduced to 1 GB, say, like very few databases. So it is easy to understand this one rather than this itself actual. So this is what they call as auto encoders, which are very popular nowadays in in machine learning. So this also we tried, and then this also works very nicely in practice actual. Okay. And nowadays, one more thing, the recent trend is, one more people are using is GAN, actual generative adversarial networks we call actual. Okay. So there are something like, if you can handle 2 neural networks, say, parallelly, and then, you solve your problem actual. Okay. So these 2 neural networks, one we call as generator here, which generates the data. Other one we call as, discriminator actually, which discriminates whether it is correct or not. And then finally, the loss function will be calculated, and we train this until your generator becomes nice and it can give you the real data set itself. So this is some of the recent developments which everybody is using in neural networks. Okay. These 2 neural networks are something like this, like this is one, image, circulated in, I followed in Google and then WhatsApp also. Like this person is blind, so this person cannot walk actually. Okay. So both of them help each other and then solve the problem actually. So the advantage is, this person, the strength of this person is something else. The strength of this person is something. You are combining 2 different people, say, and then getting the work done, so that the advantage is, there will be no bias actually. Okay. Towards this or this one. So your neural networks becomes much more perfect without any bias. Say. They can predict the data in a nice fashion actually. So in GAN also variety things have come up, W GAN, DC GAN, many things have come into here. And now you can see in 2018, this has started. Now you can see the applications are increasing, day by day itself. And these ground things are becoming very popular in earthquake early warning systems, actual synthetic data. Like once you put up instruments, automatically data comes, looking at the initial portion itself, they will give you you follow this warning itself. So the advantage is because here we are using two different networks, so the biases will be very less, and they are very efficient in generating, earthquake early warning systems and other things itself. So they have been tried for Japan, and then, so these networks also can simulate, ensemble actual of acceleration time histories, which can be used in design also as well as in earthquake early warning itself. So nowadays, now the future say, now the current scenario is, so one is a neural network actually, okay, so which does purely on data. Okay, so then we are having a scientific computing, so like, numerical methods, finite element, finite difference methods, those methods are also available actually, okay, or analytical methods say. So these are all both. So in our civil engineering say, so we use analytical method, finite element, all these things we use, and then machine learning comes with data actual. So now the idea is whether I can club these two actual, like, they are what we call as, hybrid kind of thing. Okay, some physics also is there, some database is also there actual. Okay, so combining these two, can we develop any new neural networks is the question actual. So these type of networks, let's say these are conventional things. So in ordinary thing, we have, I told you in the starting itself, we have a differential equation, boundary condition, and then you get this output. Neural network, what happens is there is no equation of motion for neural network. So for neural network, you see simply the data itself is the starting point actually. So now the idea is, can I combine these two actually, the convention with these two, and then develop something new network itself. So this is what we call as physics informed neural networks, PINNs they say. So this is it is a neural network only. So in the physics informed neural network, so what one does is, we don't use a database actually. So the loss function is not the data. Of course, sir, we use the data itself, but the loss function say is not, predicted minus this one. My loss function, I will write in terms of the differential equations actually. So like what we are trying to do is the neural network itself. So here the loss function say, we replace this loss function with this equation of motion. So your neural network, so whatever your neural network is generating the data, it should satisfy your, the equation of motion and then the boundary conditions actually. So these are very special type of neural networks, which we call as pins, physics informed, the neural networks itself. And then see, you can see here, this is a neural network here. So these are the outputs to say. So here there is no loss function actual. So we don't calculate the loss function based on the data. We calculate the loss function say based on your equations of motion and then boundary condition. So the advantage of this networks say, so these networks, they satisfy your equation of motion also. They satisfy data also. They also satisfy boundary conditions also. So these networks are much more superior to, the conventional neural networks also. So this is what we call as physics informed, neural networks. So this is what a typically neural network does, physics informed. So same neural network only, but these are the loss functions actual. The governing, like, stress sequence of equilibrium, constitutive loss, the strain displacement equations you use, and then you develop this neural network. So this has been, nowadays, recently it has been launched, but very successful. So like, for example, these are problems, a plate, with a hole, you try to find out, you see the stresses in the plate say. So ground, this is what, comes from the conventional approaches actual. So physics informed the neural networks, so it will give you this one. You can see both of them are almost, exact actual. So these neural networks, they satisfy your data also, they satisfy equation of motion also, they satisfy, the losses itself. So these are becoming very popular, nowadays, and people are exploring this in very great detail actually. And then one more neural network now which is becoming popular is physics guided neural. That is physics informed, this one, physics guided we say actually. So which combines both the models, physics based models as well as neural networks also, and come up with some nice solutions actually. So here these models, what we essentially do is, we take data also, we take physics also, and then we frame our, this loss function actually. So it is something like this. So you are having, the equation of motion also, and you are having the database itself. So what we try to do is we write the loss function like this. Okay. So this loss is empirical loss. That is the data minus, predicted by the neural network. And then we have the loss, which is based on your, equation of motion also. Then we have this error. So you combine everything and then, you try to find out the weights and then biases such that you will get nice solutions actually. So these neural networks, the advantage is they satisfy database. They also satisfy your equation of motion also, and they also will satisfy using all the possible things itself actually. So these things are becoming very popular. And nowadays, if you see recently, last year, this one's some small papers have started, people have started working in this area in civil engineering also. Slowly, say maybe in the next 5 years, you will be seeing a lot of these type of neural networks in practice actually. Okay. So fine. So I think 11:30. So I will just summarize this one. So in today's lecture, I have shown you the artificial neural networks. I have just given you a brief introduction. But please remember, the most important thing for neural network is data only. So data means, you have to do sensors. Okay. This developing new type of sensors. So then, it will be helpful for neural network. So this subject is also booming like anything. And please remember, when the data sets are very small, say, like you are having 100 tests you have done, no need to use neural network actually. Okay. Humans itself are the best. We only can take decisions. But when the data sets are very large, say, so we have a problem. But computers, it will be very easy for computer to handle. That is artificial intelligence. It can filter this database like 100 terabytes. It can filter. It can find out, like auto encoders or something. It can filter some of the useful information, which you can use it and you can do your work itself. Okay. And then structural health monitoring, this is a very booming thing actually. Nowadays, bridges, most of the tall buildings, because monitoring is very difficult. So people are using instruments everywhere. Okay. Like 500, very cheap instruments also is becoming. So now the data sets are going to increase like anything. At least as far as I know, most of the important bridges, they are getting monitored. Continuous monitoring is happening. So in the next 5 years, we'll be getting huge databases actually. And now the job of a structural engineer is, to understand this data and you have to take a decision actually. Okay. So where the damage is, what bar has corroded. So this is going to be a very booming area where I feel, neural networks have a lot of, applications in this area. And of course, in earthquake engineering, you have so many applications are there. Okay. Like now people have started using it in practice itself to find out earthquake loads and other things also. Then even in epicenter magnitude determination also, people are using, earthquake, these neural networks itself. Then even in early warning, say, right now, you see people are using these neural networks and then, in embedding in their, the computer itself to give a alarm itself. And now when you see in structure analysis and design also, people are using actual, but it has not yet come to practice level, but people are doing because of this physics guided neural networks. Say. So I hope, in the next 5 years or the next 10 years, say, which combines, your physics as well as data, and then you can get a better designs, actual better optimal designs can also be obtained from this combination of machine learning plus your conventional approaches, actually. So finally, say, so this is what, the current status, physics informed and physics guided neural networks are becoming very popular. And this may be, the key to the, the future actually, essentially in civil engineering. That's what you say I focused this on. Okay. So with this, I will stop my lecture. So I think the time is also fine. So if they have any questions, we'll be able to answer.
Yes, sir. We have a few questions on the YouTube, so I will post it in the chat box now, sir.
I hope I have stick to time, right?
Yes, sir. Yes, sir.
Maybe
Sir,
about
sir,
10
thank you
minutes.
so much for such a wonderful and informative talk on artificial intelligence and machine learning. And it's highly mathematical, sir, and your presentation was excellent, sir. I think, Aishwarya, you can post some of the queries.
I can see in the chat box, I think one Selvaraj, I think he has said some links where we can get some earthquake data to do a basic research. A lot of databases are there, NGA West is there. I will type also so that you can see NGA West database. If you type in Google, you will get these databases. Okay. NGA West, even our Pesmos database is there, which is I'm typing here. Okay. So this also you can get Indian data from Pesmos, and Cosmos is there. So these are the two websites where you can have access to Indian data. NGA West will give you, the database of whole all the world main earthquakes you can get from these NGA West databases.
Yes, sir. I have posted also, sir. Thank you.
Any other questions from the participants?
Good morning, sir.
Yes, madam. Good morning, ma'am.
This is Dr. Hemamati. Sir, I have a question like when you're explaining about that neural networks, how do you decide upon that hidden layers? We know what is the input, we know what is the out. I mean, we know the input layer and the output, what is expected. How to decide upon that hidden layer, sir?
Yeah. So one thing, madam, now if you are a hidden layer or hidden neurons, when you increase them, number of unknowns will increase. Okay. So one thumb rule is suppose if your data samples sample size, let us say you are having 100 data is there, say. So thumb rule is your number of unknowns in the network should be less than half actually. Okay. That means less than 50. That is one thumb rule you have to do it. Okay. And other thing is in the previous olden days, what we used to do is we used to do trial and error method to find out hidden layers and hidden neurons. But now I told you that one neural network has come, Bayesian neural network basically. Okay. So where you treat the weights as random variables here, if you do these neural networks, automatically it tells you, whether your epistemic uncertainty, if it is very high, so that means, there is a problem in the data or problem in the neural network itself. So you can decrease the number of neurons, and then once again you have to do it actually. Okay, so you have to do it as a trial and error only. But one thumb rule, the starting thumb rule you can see is if you are having data points, say, okay, so then the number of unknowns in the network should be less than half of it actually. So this is the first guideline you use, and then you do a trial and error iterative approaches. And if you want to know more, you do Bayesian neural network that will clearly tell you, the epistemic uncertainty will clearly tell you any problem you can get from that itself will tell you. Okay.
Oh, okay, sir. Thank you, sir.
I think some
There is one more
what is a
question.
proposed training and testing data set in supervised learning. This also I showed you. Generally, the thumb rule is 75, 15, 15. We take it. You can take it to be even 80, 10, 10 also. But why we do there's a training and testing, and I think not only training and testing. One thing you have forgotten, validating is also very important actually. Okay, so this data set also you have to divide into three portions, not into two. Training will be there, testing will be there, then validating also will be there. Okay, so now proportion is 75, 15, 15, one thumb rule we use. Okay, around that itself. And this you have to do it because so that you will not get trapped in the local minimum. I showed you in one slide, some three curves. I've shown you training, testing, and validation. So if the number of unknowns are very high, say training error will be very less, but validation others error will be very high actually. So this you have to do it 15% so that you will not be trapped in local minimum. So that is why we do this training and testing and validating also. How to choose an appropriate model for our study. Okay. So first, it depends on your data set. Okay. So if you're having very small data set, say, my suggestion is you go with a shallow neural network. That's a very small, the network which I showed you in the starting. Don't go for deep neural network. And you choose your hidden layer, one hidden layer only you choose actually. No need to go for two hidden layers also. One hidden layer itself is sufficient. And the number of hidden neurons, say, you choose such that the number of unknowns in your network will be less than half of your data size actually. Okay. So that is how you have to start with. After that, you check training, validation, this thing. Then after that, you can go for complicated networks. So starting, go for shallow neural network, only one hidden layer only. No, don't put two or three hidden layers and complicate the problem. One hidden layer and the number of hidden neurons. So you choose such that number of unknowns will be less than half of your data size.
Sir, one more basic question, sir. Sir, we haven't done anything with artificial intelligence or machine learning in civil engineering, sir. So to start with, what is the basic thing that we should equip ourselves to deliver to our students and to enrich our knowledge, sir?
The first thing is you collect data, madam.
Okay, sir.
So experimental data, right? I am not asking you to do the experiment, but in literature also, like for example, steel columns are there, say. You want to find out buckling load or something. Lots of data sets are available in the literature actually. Okay. Compressive strength of concrete. So much database are there. I showed you, right? One example, ultra that pulse velocity non-destructive testing. Routinely they do for consultancy, right? Bridges, the like 40-year-old structures, say. They want to analyze whether that structure has to be demolished or we can how much is a remaining life of the structure basically. So what they do is they do this simple test, rebound hammer, these small tests they do, and they will collect the data. So these databases are available online. Okay, so the first step is you collect all the databases, and then using these databases you can teach your students how to use that small shallow neural network to model these databases. So that is how I think you should start, right?
Thank you, sir.
Or rainfall, if you see, hydrology data sets are available, like temperature data, so daily temperature data, pollution data, people are monitoring, right? I think instruments are there, you remember, in traffic, some places they show what is the pollution today, tomorrow, like that they go on. So you collect these databases and then ask them to run a ANN for this.
Okay, sir. Thank you, sir.
Sir, good morning, sir. I am Dr. Andal, sir.
Please, Mike.
Yes, sir. Sir, what are the different type of sensors that has to be used for structural health monitoring, sir? Is any real-time example available in our
Many are there.
Chennai region, sir?
No, in Chennai
Yes,
region,
sir.
I have no idea, but Delhi, I know, madam. Well, Delhi,
Oh, yes, sir.
Bombay, right? Because there are one building which I think, some building is like almost 60-story building. So what they have put
Mhm.
is they put all type of sensors. One is wind speed they measure, okay, on the top of it, and variety of floors also. They measure accelerometers are there. Like if there is some small shaking or something happens, they measure that accelerometers are there, anemometers are there, temperature, humidity, many sensors are there. All these sensors are being used. But for if you want to find out damage or this anything, accelerometers are the best made.
Yes. Thank you, sir. Thank you.
Any other questions? If there is no more questions, I think we can wind up.
Yes, ma'am. There are no more questions in the YouTube as well.
Okay.
Can we conclude, ma'am?
Yes, yes.
Yes. Ladies and gentlemen, I extend my heartfelt gratitude to everyone who joined us today for this enlightening online session on artificial intelligence and machine learning principles and applications in core engineering branches. Our sincere thanks to Professor S.T.G. Raghukanth for sharing such valuable insights and expertise, guiding us through the intricate world of AI and ML applications. Your clarity and depth of knowledge have certainly broadened our understanding. Thank you, sir. I would also like to thank all participants for your active engagement and thought provoking questions. Special thanks to the hierarchies of management, organizers, and technical support team for ensuring a smooth and seamless experience throughout the session. As we conclude, let's carry forward the learnings of today's session into our respective fields, leveraging AI and ML to drive innovation and excellence. Thank you once again, and we look forward to more such enriching sessions in the future. Thank you.
Thank you. Thank you, sir.
Thank you, madam.
Ma'am, shall I end the meeting, ma'am?
Yeah, yes, yes.